Alright, welcome back. We're going to work on two problems today. The first one is number 6 from your handout, and it says that a 1 kilogram ball is free to slide along a piece of string that's 0.8 meters long. The ends of the string are attached to a vertical rod at points A and B, which are 0.4 meters apart. When the rod is rotated, B and C is horizontal and equal to 0.3 meters. So, 0.3 meters is the horizontal segment, 0.5 meters is up at an angle, and because our ball is free to slide, the tension in the two will be equal. So I'm going to draw a free body diagram of both and then separate my X and Y components. So I've got T horizontal and T up at an angle, G down, and my second free body diagram, force gravity and T sine theta are in the Y direction, and tension and tension cosine theta are in the X direction. So we're just going to do our sum of the forces equation. So in Y direction I have T sine theta equals force gravity, which is mg. So that's pretty good. We can use that to solve for tension later. In the X direction, both tensions, T cosine theta and T, give my object centripetal acceleration, or mv squared over r. I can solve the first equation. So T equals mg over sine theta. And in that case, T is 12.25 newtons. And the second equation, I'm just going to solve for velocity. So I'm going to multiply r on both sides and divide by m. And then I'm actually going to, it'll then be the square root of RT times cosine theta plus 1 divided by m, or 2.42 meters per second. So my velocity is 2.42 meters per second, and my acceleration is 12.25. Moving to our second problem. This says we have M1, which is 1.65 kilograms, and a box M2, which is 3.3 kilograms. They slide down an inclined plane while attached to a massless rod parallel to the plane. The angle of the incline is 30 degrees. The coefficient of kinetic friction between box 1 and the ground is 0.226, and between box 2 and the ground is 0.13. So we want the tension in the rod, the magnitude of the common acceleration of the boxes, and how would answer A and B change if the uncles trailed the aunts. Alright, first of all, we'll start off with the free body diagram of each. And we get both frictions up the slope. G cosine theta is perpendicular to the slope on both. Normal force is perpendicular to the slope upwards on both. And G sine theta is down the slope for both. That is capital G, mg sine theta, down the slope. The big difference is tension is pulling the first object downward, and tension is pulling the second object upwards. So we draw the free body diagrams, and we're going to do the sum of the forces for both in the Y direction first. So the first is force normal 1 minus mg cosine theta equals 0. For the second, force normal 2 minus mg cosine theta equals 0. So we're going to find what the force normal is for each of these. And notice we actually do know the force normal. I'm going to leave it like as the equation, but we could solve for the answer right there. Then the sum of the forces in the X direction for the first object is G1 sine theta plus T minus F1 equals M1A, and it's the same equation with a negative T for the other. We can always solve for T in one and plug into the other, but that's a little long. We could solve for T in both and set them equal to each other, but that's a little longer as well. Since I have plus T and negative T in each equation, I'm going to add the two equations. I'm going to get G1 sine theta plus G2 sine theta minus F1 minus F2 equals M1 plus M2A. Keep in mind, this is the result we keep getting, which is if we look at the sum of the forces, the sum of the external forces on our system, it is the sum of the forces equals the mass of the system times the acceleration. The big difference here is we have different coefficient of friction, so this makes it a little longer equation and a little more interesting. So to solve this equation, we're going to get from G1 sine theta 1 plus G2 sine theta 2 becomes M1 plus M2 times G sine theta, and then minus coefficient of friction 1 M1 plus coefficient of friction 2 M2 times G cosine theta equals M1 plus M2 times A. So what we're going to get out of this is A equals G sine theta minus coefficient of friction M1 plus coefficient of friction 2 times M2 G cosine theta divided by M1 plus M2. That's a mouthful, isn't it? Solving for that, we get acceleration as 3.62 meters per second squared. Plugging that number into either of the top equations, I'm going to use the second equation for no particular reason, just it seemed a little easier to solve. Add t on both sides and subtract m2a, and then plug and chug. m2g sine theta minus coefficient of friction m2g cosine theta minus m2a equals 1.05 newtons. So we have 3.62 meters per second squared and 1.05 newtons. The final question is, what if the forces, or what if the objects are reversed? Well, if there were a string between the two objects, and we reverse them, the first object with a higher coefficient of friction would have a lower acceleration. The tension in the string would go to 0 and the two objects would collide. And then they would travel down at one constant acceleration. Because there's a rod between the two, even though there's more force upwards on the first one, they will still accelerate down at the same rate. The tension will be different, but they'll accelerate down at the same rate. I hope this helps. Thank you, and good luck tomorrow.